Now we saw in the second lecture and we're introduced to multiplexers. So a multiplexer is just a selecting device. So here we can see a 2 to 1 multiplexer that chooses between two inputs. So our choosing pin or this is S, and we have two inputs D0, D1. If we have 0 on the S or in the selecting pin, our output will be the D0. So if D0 is 0, our output will be 0. If D0 is 1, our output will be 1. In this case, we do not care what the input is in the D1 pin input. And similarly, if we have a 1s on the selecting pin, our output will just be the D1. So if it is 0, our output will be 0. If D1 is 1, output will be 1. And we do not care about the D0 signal here. So then in the second case, when S is 1, our connection will be just like this. So this S pin chooses between different inputs and passes it to the output. So we can see that the expression of a mux using gates will be like this. If our selected pin is S and our inputs are D0 and D1, our output will be S times D1 plus S bar times D0. If we want to build a gate level mux using this formula here, we'll need too many transistors. So this will be our configuration. So S and D are ANDed together, so we used an AND gate, and we will need another AND gate for S bar and D0 here, and we will also need the inverter to turn the S into an S bar, and then we will need an OR gate to sum these two signals together here, and then we will get our output, which is Y equals S D1 plus S bar D0. And we also saw in our previous slides, we need 4 transistors to build NAND gate or an OR gate. NAND, NOR. And we need 2 transistors for a NOT gate. So if we just put these values in these gates, we will need 2, and we also need to build a AND gate, we need an AND gate and a NOT gate. So if we just decompose these gates into a NOR gate and a NOT gate like this, so we will have a total of 4 transistors in each of the NAND gates and 4 transistors in each of the NOR gates and 2 transistors for each of the NOT gates. So if we sum them up together, we will have 10, 20 transistors for building this kind of gate level mux. But if we use the transmission gate configuration like this, we will only need 4 transistors. So we have our input D0 connected to the input of a transmission gate, and we have another input D1 connected to another transmission gate, and both of these outputs are connected to our output Y. So this will be our transmission gate mux 2 to 1, but the problem here is that this will be a non-restoring mux, which means that if we have a noisy input, our output will also be noisy. So that is the only drawback from the previous example to this one. But the advantage of this one is that we need far less transistors than we did before. So we have 4 transistors for a 2 to 1 mux, where we had used 20 transistors to build the same thing. So which is a huge reduction in the number of transistors, and as well as consequently in the area that is required to build such a chip. So we saw that how building using transmission gates could be advantageous in terms of the space required to build such a gate, but it was disadvantageous in terms of the non-restoringness. So we get around this issue using by building an inverting mux. So what is an inverting mux? An inverting multiplexer uses compound AOI22 gates or a pair of tri-state inverters, essentially the same thing. So what we do is we connect our circuit like this or this. We can see two different implementation of an inverting mux. We will focus on the middle one. So basically this is just two inverting tri-state buffers. Okay, so this is how we connect. We have two PMOS transistors connected in series and two NMOS transistors connected in series. So one of the inputs is S and the other one is just the inverted input like this. So this is the input, and similarly this one is just the inverted input for the selector pin like this. So when the S is 0, when our S is 0, then this PMOS will be on, and since this is 0, the inverted S will be 1, and thus the NMOS will be turned on. But if S is 0, this NMOS will be turned off, and if S is 0, this is 1, then this PMOS will also be off. So basically this portion here is in the Z state, meaning this output will be floating from this device, but but we can see on the first tri-state buffer these two transistors are conducting. So this will act as an inverter, and we will get an output of Y equal to D0 bar, D0 bar. And so if we have a 1 in our input, or our selector pin S, then what happens? We can see that if S is 1, then this PMOS will be turned off, so this one will be off, and similarly this S bar will be 0 and this NMOS transistor will be off. So our this tri-state buffer will be in the Z state, meaning this device will be in the floating state from the output Y. But if S is 1, then this NMOS will be conducting, turned on, and this S bar will be 0 and this PMOS will turn on. So we have a connection between this D0 and this D1, and so this buffer will be acting as an inverter. So we will have an output of Y equal to D1 bar. So we can see that by using two tri-state buffers and connecting their output together, and by choosing the selector pins accordingly, we can create a 2 by 1 inverting mux. And so this is the symbol of our inverting mux. We have a bubble here to indicate that this is an inverting mux, and we can also see that this has very far less transistors than our previous one. Let's count how many transistors we have. We have 1 2 3 4 5 6 7 8, so 8 transistors for the inverting mux. And if we want to convert this into a non-inverting mux, then we will have to connect a NOT gate here and get its output. So even then we will need only 8 plus 2 equals to 10 transistors, whereas we had used 20 transistors in the gate level design. And similarly, by connecting in two levels of 2 3 2 to 1 muxes, we can create a 4 by 1 mux. And on the right hand side we can see that our implementation here, this is just from building using 4 tri-state buffers. So this one is a tri-state buffer, this one is a tri-state buffer, this one and this one, and we use two signal pins S0 and S1. So if we have 0 0 in S1 and S0, this signal will be 1, but this all of them will be 0. So this buffer will activate and will output this one, but all of the other buffers will be in Z state. So they will be disconnected from the output or will be in a floating connection like this. And on the left hand side we can see that this is another implementation of a 4 by 1 mux. So we use 3 2 to 1 muxes. So in this case we will need 6 tri-state buffers, whereas in the right hand side we needed 4 tri-state buffers. But on this one we have the advantage of this being an non-inverting 4 to 1 mux, but on the right hand side this one is indeed an inverting 4 by 1 mux.